Hey guys, Mr. Barnes here. I'm going to bring you a little spring video you guys have been requesting for the past couple weeks. And I know a bunch of you guys during study hall yesterday mentioned it as well. So we got a massive 0.4 kilograms is stretched on a spring with a spring constant of K is equal to 150 newtons per meter. So this is the units per spring constant, so newtons divided by meters. 0.15 meters past the equilibrium point. How far past the equilibrium point on either side is the mass when the potential energy is half the kinetic energy. Alrighty, so what we need to know here is how much total energy does the system have. So again, we know that the total energy is equal to kinetic energy plus the potential energy, which in this case is actually elastic potential energy. Okay, and the formula for that is 1/2 kx squared. All right. So what we need to know is when is the kinetic energy. What is the mass when the potential energy is half the kinetic energy? Alrighty. So let's calculate how much potential energy is in the system initially. And of course, at the beginning, when the spring is fully compressed, that it's all potential energy. Okay. So that means that at that particular point, we have all potential energy and zero kinetic energy. So that means that energy in the system total is equal to the potential energy. So let's see what that is. So we got the energy potential is equal to 1/2 K, which is 150, x squared. So 0.150 squared. So let's break up my WABANEMU here. And we got 0.150 squared times 150 divided by 2, and that's 1.69. So we got 1.69 joules. Alrighty. So this represents not only my potential energy, but it also represents my total energy as well. So that's the total energy for the system. Okay? So we're interested in when potential energy, when the potential energy is 1/2 the kinetic energy. So what that would look like is that EK is equal to 1/2 EP. Alright? So we know this. Okay? So let's write out what we got here. So we got the energy total is 1.69 joules. The EK, of course, is just my EK. And my EP is my EP. Okay? So we know that the EK is also equal to 1/2 EP. So we got 1.69 is equal to 1/2 EP plus EP, or 1.69 is equal to 1.5 EP. So now I can substitute in my EP, 1.1/2 K x squared. I don't know what K is, or sorry, I don't know what X is, so that's what we're trying to find. So we got 1.69 is equal to 1.5, 1/2 times 150 x squared. So let's do a little math here, so I'll simplify this a little bit. 1.5 divided by 2 times 150, whoops, times 150. Okay, so we got 1.69 is equal to 112.5 x squared. So let's calculate x squared. So we go 1.69 divided by answer, and then that's 0.015, and then we take the square root of that, square root of my answer. So we get x is equal to 1, 2, 3. 0.123 meters. Okay, so that is the position at which kinetic energy is twice potential energy, or potential energy is half the kinetic energy. Okay, so that was a tricky problem. Now, if you want to check it, you can sub in the numbers and see if it works. Okay. Now I know they gave you this mass in this problem, so I don't know if you could solve it a different way using that kinetic energy somehow, 1/2 mv squared. But you know, I think the way I did it here was pretty neat. So again, try it on your own, see what you get. All right, next problem: work, energy, and springs. So this one's a little different. Again, what I would do right now is I'd pause this video and try it on your own, then see what you get. A block with a mass of 5.7 kilograms slides on a frictionless surface with a speed of 1.2 meters per second. It is brought to a rest by spring in its path. By how much does the spring compress if its force is constant? If its force constant, what's the spring constant, is 1,500 Newton meter. Okay, so what we have here is a situation where we're going to have to use work energy theorem. Okay, you got a speed here, and you got a block with this mass moving on a frictionless surface. So the maximum amount of energy that this initially has is when it has this speed of 1.2 meters per second. So let's calculate the energy here. So the energy here is equal to 1/2 mv squared, which is equal to 1/2 5.7 1.2 squared. So go to my calculator here. So I got 1.2 squared times 5.7 divided by 2, and you have 4.7, or sorry, 4.1. 4.1. That's good enough. So 4.1 joules. Okay, so that's the energy total that it's initially going with. Now, so as this block hits the spring, it does work on the spring. And the amount of work that it does on the spring is going to be equal to the change in kinetic energy. Okay? So the change in kinetic energy, of course, is going from 0 to 4.1. So that work is also equal to 1/2 kx squared, which is the elastic potential energy. So to find out how much the spring is compressed, we know that it's 1.4 joules of work that happened. Okay, because the work is equal to change in kinetic energy. It went from 4.1, nothing, and then you could have a negative in there, but it's just going to cancel it, so don't worry about it. You got 1/2 15 Newton meters, x squared. So then we're going to solve that thing for x. So I'm just going to do my workings on my calculator here. So I'm going to go 4.1 times 2 divided by 1,500. So that's x squared. Now I got to take the square root of that to get x. And I get x is equal to 0.074. 0.074 meters. Okay, so remember that there's a very close relationship between work and energy. All right, and that's brought to you by the work energy theorem. Alrighty, last problem. Okay, This is similar to the other one here, except we got a few other things going on here. So pop-up toy has a mass of 0.02 kilograms and a spring constant of 150 Newton meters, as shown. A force is applied to the toy to compress the spring 0.05 meters. Calculate whether the toy will hit a 1.2 meter high ceiling when it's released. So this is a problem that we went through in class, came from an old exam. So here's what's going on. At the very bottom, it's all potential energy, okay? When it reaches the top, so that you got to recognize that this thing is flying off here. When it reaches the top of the maximum height, it's all potential. So all that potential, or all that elastic potential, has been converted into gravitational potential. So we got to sort of label our stuff a little different this time. So my energy total, in this case, is going to be my elastic potential plus my energy potential, okay? Or sorry, my gravitational potential. I should call that EG. All right, so let's calculate the energy elastic initially, which is the ET as well. Okay, so I got my 1/2 K x squared is 0.05. That's how much it's compressed. So do the math. Don't forget my squared there. I'll put it in a second. Squared times 150 divided by 2. So I'll run my squared in before I forget about it. So 0.19 joules. So that's the total amount of energy in the system. So I know when it reaches a maximum height that it's going to still have 0.19 joules of energy. So 0.19 joules. That's going to be equal to mgh. Okay, that's my gravitational potential. So 1.19 is equal to m, a mass of 0.02. Gravity, call it 9.8. And my height, which I'm looking for. So we do the math on that. 0.19 divided by 0.02 divided by 9.8 gives me a value, height, of 0.96 meters. So we're looking at, no, it's not going to hit the ceiling, okay? It will not hit the ceiling. It's not quite high enough. Alright guys, hope this helped. Thanks a lot for watching.